The last tree traversal algorithm we are going to talk about is post-ordered tree traversal. And here again, you dissect your tree as the subtrees and the root. So this is the leftmost subtree, this is the second subtree, and this is the rightmost subtree, and this is the root. In post order, what you do is you go through the subtrees first and the root last. Okay, so again, this is recursive. Therefore, you will process this subtree first and then this one. So this is number 1, this is number 2, this is number 3, and this is number 4. But in number 1, you see we still have a subtree. So the leftmost subtree is here. So this will be 1.1. Then you do the other subtree, 1.2, and the root of this is 1.3 will be lost. And inside 1.1, again recursively, this is the leftmost subtree, so that will be 1.1.1. And then this will be 1.1.2, and the root last, 1.1.3. And inside 1.1.2, N will be first, and then O, and then P, and then K, and then you backtrack. So let's see how this works out. I'm going to visit the leftmost subtree first, and inside it, again, recursively, I'm going to visit this left subtree first, and then this left subtree first. So J will be the first to be visited. And then I will move to this second subtree, and inside this subtree, the leftmost subtree is N. So that will be the first one to be visited, followed by the other subtrees, O and P. And finally, I visit the root of this subtree, K, and then go back to the root of this subtree, which is E. Then you see, since this is done, I will go to the next subtree, which is F. When it is visited, I go to the root of this. And when I visit the root here, this will be done, and I should move to this next subtree here. Visit C. Since it's just a leaf node, it's done, and move back to this rightmost subtree. And again, recursively, go to the leftmost subtree, go to the leftmost subtree, you get L, and then the next subtree, and then the root G. And since this is done, go to the next subtree, which is H, and then I, and finally the root of this subtree, which is D, and afterwards the root of everything, A. So this is how you visit a post-order, how you perform a post-order traversal on this tree. Now we have seen all three traversal algorithms here, and let's see some applications. And these are particularly useful for parsing. We have the concept of expression trees or parse trees. If you have taken, for instance, a compiler course, compiler design, you have such structures to evaluate expressions in your software. So you build an expression tree and you evaluate it in a certain order. Now, we have what we call prefix expressions and postfix expressions, and a Polish notation for elementary arithmetic, and the reverse Polish notation are very widely used examples, typical examples to these. And the expression we have here is, well, you see we have B minus C here, multiplied by A, and that is added to this here, which is D plus E. Okay, now this expression can be expressed using Polish notation or reverse Polish notation using without using any parentheses. That is the advantage of such expressions. You don't need parentheses. Without parentheses, the expression is not ambiguous. Now, if you drop the parentheses here, it will be ambiguous, as long as you do not really assume any precedence. But if you have the Polish notation here or the reverse Polish notation, they are not ambiguous like the one with in order. So here, this tree is an expression tree. If you traverse it pre-order, okay, this first plus, and then multiplication, and then A, one operand, and then minus, and then B, and then C, and then A plus, and then D, and then E. Okay, and with simple applications, this is another example for using a stack structure. Again, you can look it up, but you can also use an expression tree of this sort to build a prefix expression when you traverse this expression tree in pre-order. Or if you traverse it post-order, in this example, it will be A, and then B, and then C, and then minus, and then multiplication. Then to the right subtree, you get D, E plus, and then plus. Okay, so this will build you a postfix expression if you traverse this expression tree in post order. Now, if you traverse it in order, it will be leftmost first, and then here you have A, and then the root, multiply, and then you have this, so B, the root minus C, and then the root plus, and this subtree, you take the leftmost subtree first, D, and then root, and then E. Okay, so again, this gives you the same expression, but you see this is ambiguous if you don't have either precedence or parentheses. So what we want here is obviously B minus C like so, and this is like so. But the parentheses are not visible in the graph. So in such a case, prefix expression or postfix expression will help you express this operation in an unambiguous manner. Another application is in binary search trees, especially with in-order traversal. This is the example from earlier. Now, if you apply pre-order or post-order traversal to this, it doesn't really do much for you, but see what happens when you apply in-order traversal. You visit the leftmost subtree first, and to do that, you visit again recursively the leftmost subtree, which is 1, and then the root, which is 4, and then the rightmost subtree, 5. Now this is done, so I visit the root next, 7, and then the rightmost subtree. And inside this, recursively applying in-order traversal, I need to visit the leftmost subtree, and inside that subtree, the leftmost subtree is 8, and then the root, and then the rightmost subtree, and then the root of this subtree, and finally the rightmost subtree, which is 16. Now, when you look at the order, you see it is in order. So that's the reason we call this in-order traversal. When you traverse a binary search tree in order, what you have is really the key values in order.